So, Booking.com, we're a large website. We want to store a lot of data on people, and we do some of that in cookies. So let's talk about that. This is working, hooray! So this talk, I'm going to talk about what we do at the moment. I'm going to talk about some problems with what we do at the moment. I'm going to talk about the system we designed to solve those problems, and then I'm going to ask for questions. But I don't think I actually have a slide that says questions, so oops for me. Cookies. Everyone knows what a web cookie is. Client-side data. Not actually a lot of space. We only have about 4K in there. At Booking.com, our cookie is schemaed and heavily compressed and encrypted, and we're totally running out of space, which is too bad because we want to put a lot more stuff in there. In addition to cookies, which are client-side data, we also have server-side data that we store for people while they're browsing the site. We don't have the 4K limitation. The limitation is really just how much hardware we can throw at the problem. At the moment, we have lots of serialized Perl hashes with serial, and they're large K, sort of about 20K on average, and they live in memcache, and that gives us very fast access to them. But that means when the cache expires them, because they haven't been browsing for an hour, or the memcache server goes away, so does all that data. So it's not really persistent, and that makes us sad. Cookies themselves, as I said, they're persistent, but they are linked to a particular device, not linked to a user that actually comes and browses our website. If the user clears their cookies, or if the user uses a different web browser, or if the user comes to us on their tablet, or comes to us through one of our mobile apps, we can't get at the cookie that we have stored on those other devices. And as I mentioned, we are running out of space. We have done an awful lot of very tricky things to cram everything we need into that 4K cookie. But there's just so much you can compress into 4096 bytes. The other problem we have is sometimes you want to update some user's information, but you can't because it's in the cookie, and they're not currently actively browsing your site in the middle of a page view. We have a lot of asynchronous processes that we run. Maybe we want to do something when we send out an email to a user, because their reservation has just happened, or they've contacted customer care, and we need to do some of that processing, and we would sort of like to update some sort of profile information that we have in the cookie, but we can't because they're not. We are not processing a request. We don't have that cookie sort of in our hot little hands that we can modify and shove back to the user. So what we decided to build is server-side cookies, which is the same kind of unschemaed, compressed data that we can store, but it's persistent. We don't have the same limitations as with memcache when things would go away. So they're persistent data. We still give it a session ID, much like a traditional session that we would be storing in memcache. But for us, it was actually more of a platform that we could use for sharing unstructured data across devices, across browsers, across tablets, various desktop things, and on our mobile apps. So constraints, because if you just say build a system, that's not really interesting. Our constraints is that Booking is very, very big. And so we had some hard limitations that we really wanted to sort of design the system within. The first one was it had to be really fast. Our page views we do a lot of processing already. Our page views are not as fast as they could be for a number of cases, and we didn't want to slow that down. So we said, let's have a hard cap of 5 milliseconds latency for talking to the system and getting data back out of it. We have projections of about 40 terabytes of storage. over the next couple of years. So we had to design a system that was going to take a lot of data and could store it in a way that we could get at it quickly. It had to be horizontally scalable. At Booking, we are totally at the point where we cannot just throw more hardware at our problems. There are many cases where you say, well, this system is a problem, but next year's computers will be faster, and we can just throw those at it. Booking.com, we are too big. That doesn't work anymore. So we had to plan this to be horizontally scalable, so we could throw not bigger boxes at it, but throw more boxes at it, sort of scaling up horizontally. In line with that, it had to be fault tolerant. If we were storing user data, we didn't want a failure of a single machine to cause a significant loss of data, because that would be a lot of data for a lot of users, and that would make them unhappy. So we were going to have any single box would fail, and we would still be fine. We were actually moving to multiple DCs, data centers, so same kind of thing. A single data center could fail. We could lose all the boxes in the data center, and it still had to work. We couldn't lose any user data. Sorry, sweetie. Some of the technologies that we use already, Memcache. We currently store user sessions in Memcache. It works great for that, but it's not persistent, right? The box goes down, you lose all the data. Secondly, where do we get 40 terabytes of RAM? That's quite a lot. That's a lot of boxes. So that wasn't going to be particularly useful for us. MySQL. Booking.com, we use MySQL a lot. We have about 2,500 MySQL servers. And we could totally store 40 terabytes in MySQL. Still too much for RAM. If we ever have to hit the disk, we're going to be too slow. So everything had to be in RAM. But that causes a problem, because if you have 40 terabytes of data and you have users coming and visiting you, you're going to be hitting disk a lot, because your cache in MySQL is going to be loading up totally unrelated records, and we are not going to hit the 5 millisecond latencies that we needed. Secondly, we can't handle the write load. MySQL is good, but the system that we were designing for, we wanted to hit 50,000 write transactions a second. You can't do that with MySQL. I think we did the numbers. We need about 85 MySQL masters with 7 very large disks each to handle the write load. We do sharding, but that's a little bit excessive for this system. We couldn't just throw SSDs in it, because at 40 terabytes, that's a lot of SSDs, especially if you're trying to make them redundant and you're trying to make them fast. So that was just simply not cost effective for us. We looked at a number of existing key value stores. We evaluated a number of them. Most of the existing solutions are either optimized for write throughput, or they're optimized for analytics, sort of after the fact, which meant that if I just needed to get a single user's key, again, it was not going to fit within the 5 millisecond latency that we needed, and also have the 50,000 write transactions a second. So, I bet you're wondering, what did you do? The solution that we came up with is MongoDB.
Really?
It's
getting really worried.
So the solution we came up with is Redis as a hot cache backing MySQL. And to get those things to talk together, we added 0MQ and C and quite a bit of Perl to actually tie it all together.
Can I ask a question?
Yes.
Did you consider Elasticsearch and replica shards?
We use Elasticsearch for our search clusters.
So using Elasticsearch for this kind of data here, and basically using for the ID retrieval would be overkill. Like for the,
yes, but
so at that point, not only that, there's still a lot of weird cluster semantics and some strange in cases that we fall into. That we have to call up like Shai Bannon and say, hey dude, our clusters are now doing weird things, and take a look at it.
Right, but you did take the possible solution into account, I wonder.
No, because it would be like swatting a fly with a thermonuclear weapon. That works, by the way.
You did have a lot of demand, so it could have worked.
Why do we settle on Redis? First of all, it has persistence built in, which is very useful for us. So the box goes down. We have snapshots, so we only lose a snippet of the user data. And in fact, we can reduce that because it has replication. So if a box goes down, we actually switch over to the slave, and now we haven't lost any data. And third thing, Redis, you can store structured values, which was very useful for us. And I will talk a little bit more about what we are actually storing in Redis. But it meant that we could store the user data along with some metadata and still get at the metadata without having to actually unpack the entire user data blob that we had stored in there. Why MySQL? Because we're really good at MySQL ops. Like I said, we have about 2,500 MySQL slaves. We can bend and twist MySQL in all sorts of crazy ways. We're really good at this. I think switching to another persistent store just didn't make sense for us to drop anything else in. Why do we choose 0MQ? So, that was a mistake. So, let's see, my worst technical decision ever, that's Stephen Muller. 0MQ is a horribly leaky abstraction with a propaganda as documentation. Yeah, Nick. That actually got retweeted by the 0MQ guy. So, it was not useful for us. I don't have another 40-minute talk to go into why, but you can find one of us at the booking booth, and we will explain to you in detail all the use cases that didn't fit for us.
Bring beer, because it requires lots of that.
So here is basically what the system looks like. I will talk about what a full request sort of loop looks like, but basically we have, so these are our web boxes here, talk to a broker that is written in C. That hands the request off to one of the workers that queries Redis. If it's not in Redis, it'll query MySQL, and then sort of spits it back. And we have expiry workers that move keys from Redis into MySQL, and the workers talk directly to the remote DCs to do optimistic replication and to do lookups if they don't have the data that was there. So, protocol. Some issues that we encountered. We used a binary protocol for more speed because we needed more speed. So we used lots of pack. They were very ugly. You can go see Nick's talk later this afternoon about building binary protocols in pack and when you should or should not do it. Of course, we didn't have his talk before we wrote our protocol, which is why we have the talk now. Our protocol was not as straightforward as it could be, which meant that we had very complex pack and unpack strings to basically take all of our fields and create our binary packet and shovel it along. UTF-8 in binary data, oh my god. Interesting to note, I think I mentioned this in bugs later on, but this was actually a problem for us. Stuff with the UTF-8 flag being on or the UTF-8 flag being off in binary data and marshalling, and this was terrible, don't do it. I wish Perl had a better way, but it was very, very tricky. Heartbeats. So, interesting thing about 0MQ is there's no way to tell if the remote end is there or not. So the thing you're supposed to do is have heartbeats going back and forth between all of your workers over your communication channels. And with our setup, with our 250 workers, our broker was doing too much time sending heartbeats back and forth to all of the workers to actually do any work. So that wasn't useful. That was one of the issues we have with 0MQ. The complex pack and unpack strings were difficult to construct by hand, but we had to do it because that's what we had. Pack is an insufficiently powerful language to make any kind of complex data structure out of. Building a statically typed network protocol in a dynamically typed language doesn't work that well, which is too bad because we needed that. And that was source of another set of bugs. And I don't think we really needed a DSL beforehand to implement the protocol rather than using Packer. So that was a problem. Edge cases. There's an awful lot of edge cases when you're building a fault-tolerant distributed system. And you have to handle all of them. Timeouts, retries, failovers. This is not a place where you can just say, well, I'm going to do this and I will let my exception sort of bubble up to the top and then die with an error message. This is really every single network call you can do that has that can potentially block. You have to poll and have timeouts and have returns and have sane error messages, because everything is we're expecting, I'm either depending on a response or I'm depending on a failure, but I need to know what's going on. We can't have workers sort of failing in the middle of requests because that request isn't necessarily going to get retried. Or we have to make sure it gets retried, which means that there are multiple retry loops at every single point in that chain that I showed you as the request goes all the way through the system. Bugs that we encountered. Yes, pack and ASCII strings. So interesting bug. That was about a week of staring at hex dumps. If you have an ASCII string that happens to have the UTF-8 flag on, even though it doesn't actually contain UTF-8 data, and you pack that with v/a, then the resulting pack string has the UTF-8 flag on, which is totally incorrect. And if you try and print out the string like as a hex dump, then it will happily display not the UTF-8 data, because it will unencode your UTF-8 data, and you will see the bytes that you expect to be there, but not the bytes that are actually in the buffer, which then gets sent across the network link. And that was not fun. So don't do that. We found a very interesting bug in. Sorry.
Oh, this bug.
This one. So so everything is very heavily sharded, and we'll talk a little bit about that more. But we're using algorithm consistent hash Kedema, which is a consistent hashing algorithm, which lets you basically you have 5 servers and you use the consistent hashing algorithm, and then you add a 6th server, and the keys are magically distributed across your 6 servers now, so you can sort of expand and contract your sharding setup very easily. But there was a bug in algorithm consistent hash Kedema that we found. And when we were using we were using one way of generating our IDs and then hashing them across our servers, and that was working great. And then we changed the way that we were generating our IDs, and we sort of turned this on and ran it through some traffic for a little while. And when we actually looked at our database load, we noticed that's interesting. All of our 80 MySQL shards, 79 of them are empty, and one of them, shard number 78. Has 20 million, I think 72 million keys in it, which was not actually as evenly distributed as we had hoped. And that was basically because all the keys we were generating began with a null byte, or a 0 byte, and algorithm consistent hash Kedema accepts a C string. So
without a link. Without a link.
Without a link. Yes.
I wondered if it was on def error. It just sounded like.
Yeah. So that was interesting. So let's look at the actual protocol. What we actually sent through for this. So this is one of our very simple pack strings.
It's gorgeous.
Gorgeous. Yes. So what we said, we say set cookie, and that will basically go from our web server across to the broker, across to the worker, to unpack and deal with. We have some boring header fields, some version of the protocol, what type of request is this, the version of the cookie itself. One of the other things you learn with dealing with distributed systems is you get lots of race conditions, and race conditions are a pain in the ass to deal with. And one of the ways that you can sort of figure out what's going on is to sort of version all of the data that's coming through. So we have a version of the cookie, of this particular version of the cookie. So the next write will increment that version. So if we see an old write coming through, we'll say, well, wait a minute, your data is too old, we're going to throw it away. So the actual cookie ID that comes for the categories. So we have a number of different applications that we're running that we want to store data with. So we can say, well, this is information for some of our XML servers. This is information for some of our mobile apps. This is information for maybe the touch version of our website, or this is information for the main desktop version of our website. The temporary and durable, this basically is how we have extended the session semantics that we would otherwise have. So the cookie contains temporary information, which is stored in Redis, and it contains durable information, which is stored in Redis, and then is what is persisted to MySQL. So that means that we can have sort of more data which is available, and then at expiry time, we say, okay, well, we don't actually need all this stuff. We're only going to save these parts of the server-side cookie key. And that works well. And in order to deal with our cross-GC replication, we have a list of data centers that we're going to replicate to. So that's that one going down. Yeah. So to be more explicit about what actually happens on a set cookie request, our app server here says I have some user data. I need to save this, so it sends a request off to the broker. The broker will then forward that packet directly to one of our workers. The worker unpacks the packet, says, which machine do I need to talk to? So you see here we have, I think, multiple Redis machines. Those Redis machines, we actually have, I think, 6. We have 18 Redis shards, but they're actually they're actually master-slave pairs. So each of those machines is actually behind a pacemaker setup for essentially failover. So we have, I think, like 2 or 3 second failover if a Redis machine goes down. Same with the MySQL machines. These are all in master-master pairs with a virtual IP controlled by pacemaker to instantly fail over. Well, again, 2 or 3 seconds in case of failure on that side. So the worker looks at the cookie key, says, I need to go set it into this particular Redis shard, and it writes in, again, basically the data that we have. The version, the durable data, the temporary data, and the category. So that's very happy. And that one always succeeds because that one always writes to Redis. And I'll talk about the remote DC stuff in a little bit. A get cookie request is a little bit simpler. Again, this time we don't have any of the data. We're just saying, please try and fetch this version of this cookie from these data centers. And that returns. And so when we come in, the worker, it'll check its local Redis. If it's not in the local Redis, it says, well, maybe it's in the local MySQL. If it's not in the local MySQL, then it'll do a request, again, off to the remote DC that is listed. So let's talk about expiry. So we had to hack Redis on expiry to send a notification to our expiry process, and Stefan did that, and that's on GitHub. Basically, we have a script. Yes. I have the thing. No, I don't. So basically, what happens is when Redis says, "I'm all done with this key. I haven't seen any requests for it in 8 hours. Let's assume this browsing session is done." It sends a notification to the expiry handler, and again, there's actually, I think, a dozen of these processes running. The expiry handlers, in order to reduce the write load on the MySQL instances, group together keys by their shards. So for example, rather than doing a single write transaction for each of the expired keys, it does batching. It says, well, I'm going to wait until I have 1,000 keys that have expired for MySQL shard 1 before doing a write, boom, as a batch. And then, again, reasonable timeouts. If I've waited, 10 seconds and I only have 400 keys, I'm going to write those because I don't want this data to go down. So that handles there. The other thing that we can do in our expiry handler is other kinds of logic. So for example, if we needed to look at the temporary data and do some sort of aggregates on that before updating the durable key, well, we can do that in the expiry handler. and other sort of discarding. You can say, well, you know what, this is probably a bot from, the user agent is Google. We don't need to actually store this in our data center. Or we don't need to persist this into our MySQL store because this person's probably never going to come back, or whatever sort of metrics we can do. So I mentioned sharding. We do everything is heavily sharded here. Like I said, we have 18 Redis shards and 80 MySQL shards. That works very well for us, keeps the write load down. It's very nice that we can just add another Redis server, and 24 hours later, we now have, instead of 18 Redis shards, we can now have 24 Redis shards across all of those servers. So consistent hashing, it's awesome. Look it up.
In our particular case, with the consistent hashing for Redis in particular, we do passive key migration. So what consistent hashing gives us is the ability to only migrate like n divided by k amount of keys when you add or take away a particular shard. In our case, using Redis, since everything expires anyways, we actually maintain 2 continuums, and then we can check each continuum as we're going, and eventually one continuum will be completely drained of keys because we're only writing into the new one. So it actually works out really well when you want to add capacity to the basically to the Redis part of the system.
Right. Do you use the notification of expiry to balance things?
No, we don't. We just wait a day.
Yeah, it'll fall out on its own. There's no need to do anything active in that regard.
It's totally magic. It's brilliant.
Yeah.
Not sure if serious.
Yeah.
Oh, no, serious. Absolutely.
Multi-DC support. So we have multiple data centers at Booking, and our replication, so we have optimistic replication that we do. If somebody gives us a set, we just forward that set on to the remote data center and hope that it sort of deals with it on its own way. It's a fire and forget. On a GET request, as I mentioned, if we don't have it, we ask the other data centers, hey, do you have this key? Because I kind of need a copy. If we do have it locally, then we send the GET request anyway across so that the remote DC will pull its version of the cookie from its MySQL server, so that if we do have to fail over the data center, the Redis machines in the other data center are already hot with the data that was in the data center that just failed. So that's nice. So if anybody sort of studies sort of distributed systems, there's the whole CAP theorem. Distributed systems are hard. Consensus can't be done quickly. We can't guarantee that everybody has the data, so we're very optimistic about these replications. But with the multiple writes going on, I think at worst we're probably going to just lose the keys that were actually in flight when the data center failed, which means we are at most 1 or 2 versions out of date. But for us, that was something that was an acceptable loss. I think if we lose an entire data center, some versions of some users' keys that are active on the sites, losing those, that's where we were fine with that. We were going to have bigger problems.
What would be a realistic worst case latency?
Our write. A single request, if it's in Redis, is about 5 to 8 milliseconds. So we basically hit that. We were really happy. If we have to go to MySQL, it bumps to about I think 12 to 17 milliseconds. If we have to go cross DC, if it is in the remote DC's Redis, then we jump up another, I think it was 22 to 24 milliseconds, and if it's in the remote DC's MySQL, then we're at sort of 20, 28 milliseconds. So I think with our system,
So worst case, the way that we do the timeouts is I think we give like a 50 millisecond timeout for like each step along the way.
Yeah, something like that.
Yeah, so like worst case for if we exhaust the entire system and we hit timeouts all along the way, it's still only, I think, it's less than a quarter of a second that we wait before we reply.
Right.
and say, hey, we don't
There
have
we reply with nothing and return an empty cookie and let the website know, hey, we didn't get any cookie for you. Here's an empty one that you can fill in, but we're probably not going to save it because we didn't actually read anything for you, and our data center isn't up and working at the moment.
Right, the next request will probably be, because it's all being fetched and stuff.
Well,
Yeah.
it depends. Like if the cookie, if for whatever reason that there is a catastrophic hardware failure and we end up hitting all of these timeouts and we happen to resolve it, then yes, absolutely.
Yeah. And I think all the pacemakers basically flip over, because we've tested this. All the pacemaker setups flip over in about 5 to 10 seconds. It is too long, and they're working on it. The problem is the pacemaker does the Redis shutdowns in serial, and we need to parallel. But that basically means that if we have a machine failure, the virtual IP switches, and on the retry, it'll hit the new machine, and that one should be up and working. So in case of machine failure, we have about 10 seconds of downtime, sort of at the worst case. It's really DC failover that is the big one for us, but that's going to be a big one for anybody. So distributed systems are hard. Race conditions. There are so many race conditions. People so many requests in flight. People with browsers that are waiting on a single image before actually sending the next request, or people that go down a list of hits and open a dozen tabs, and now you have a dozen in-flight requests that come in, and it's like, well, which one? How do you say I'm going to deal with these in order? What is order? How do you build a total ordering of your system? You can do it, but that requires locks. That requires forcibly serializing all these requests, and that would create unacceptable page latencies for the people that do that. Edge cases. Oh my God, there are so many edge cases.
The state table for this system is phenomenally complex.
Yes. Again, distributed systems are really hard. It's one of those things people say. C programmers never check their return values. If you're building a distributed system, you have to check every single return value. You have to always think, this thing might fail, or this thing might say it succeeds but comes back with an empty request, or this thing might actually send an exception, or this thing might send a timeout. And you have to deal with those always, and there's a lot of them. When you sort of look at this code, it's like, well, it's not actually a complex system, right? You do a write to you do a write to Redis, and on a read, you do a read from Redis, and if it's not there, you do a read from MySQL. Right? That sounds like a very easy program to write, but it's really all in the edge cases. It's all in the sharding. It's all in the timeouts. It's all in all the other things that actually turn hey, this is a pretty easy idea, into this has to be a production system. And not only does it have to be a production system, this is a no turning back system. If we turn this on, all of a sudden, we are now saving user data in this new system. And if we say, oh, this doesn't actually work because we need to turn this thing off, well, that's kind of a problem, because now we have user data in this. So maybe we say, well, we're going to ignore all that user data that we saved. But that means you have to consciously make that decision. I'm building a system that at some point I'm going to say, even though we've deployed it, we're going to lose all the system because we found a bug in it. Something else that we dealt with is you deploy a system and it's working great, and then you realize, oh, well, we do actually need to do this because of this other bug. But now you have 20 million cookies out there that have subtly incorrect data in them, and when you wipe out all your existing data, those users are going to come back and say, well, hey, where's my data? And your system is going to say, well, I don't have it. And so you need to build your system so that it can say, well, is this I don't have your data because you never gave me any data? Is this I don't have your data because the system is currently down and it's not working? Or is this I don't have your data because I had your data and then I deleted it? Those sort of generate different areas of warnings, right? If we saw a spike in warnings of failed to fetch key, well, that's really a problem. Until we noticed that everybody was actually, these were all 8-hour these are all page views that occur, or these are all errors that occurred more than 8 hours after their previous page view, and they had expired, except they had only had a single page view, and so we thought they were a bot, and so we deleted their user data, and then they came back.
You know what this needs? The picture of the cat that says, I made you a cookie, but I eated it. Going back to edge cases, there's, the easiest part, the most reliable parts of a system are the ones that aren't there. In production, there are a lot of systems there. There are a lot of pieces that are there. So interesting, here we go, some metrics. How much code? So, about 9,000 lines of Perl. Almost all of that is error checking. We've got 2 modules out of that on CPAN. Sharded KV, which is the sharded key value store with Redis and MySQL backends. And again, using the algorithm consistent hash Kedema that has options for key migration. And we basically just use directly that from CPAN. So that was Stefan. And Nick, we got reflexive ZMQ, which is reflex bindings for 0MQ, which works sufficiently well for us. I think the worker uses that, and
that's it.
Right, yes, the main web app does not. The web app is just using the 0MQ library. So the broker, that basically is just shuttling messages back and forth between the web app and the workers, is about 600 lines of C. And I wrote about 1,000 lines of Go code for basically testing the application. Basically, our load tester was written in Go. Re-implementation of the protocol, super handy. If you're building a binary protocol, if you can get 2 independent implementations, it's fantastic.
So you find things like the UTF-8
because then so then you find weird error cases in your initial implementation, things that you didn't consider. Just building up sort of compatibility, things you didn't thought, error cases that you didn't take into account because both systems are doing the same thing. But if one of those systems fails and starts doing something else, then you actually need to handle that. So that found a number of bugs. And again, that was a module that I wrote to make the binary protocols easier. That's a Go BinPack. And as part of this somewhat, but not, I was also egged into building the initial serial implementation in Go. And that is on the serial repo, and that works very well for us. So, in conclusion, distributed systems are hard. Large distributed systems can totally be built in Perl. You can do it. And don't use 0MQ.
Instead, do...
Sorry?
What is your recommendation?
Recommendations.
Okay, so if we had to do it all over again, we would have said, fuck it to 0MQ, and we would have managed the socket multiplexing by hand.
Okay.
Because really, that is the only reason why we did it initially is that it supposedly handles everything magically in threads, and you don't have to think about it except for you
except that it doesn't
have to think about it.
I'd like to talk to you about it later.
Yeah, and I think the real thing is just that if you are building a very simple system with 0MQ, then you can use it. It works great. It's a networking library. You can sort of build some stuff up. The problem is if you're building a complicated, actually distributed system, then you need to think about a lot of error cases. You need to think about a lot of edge cases, and 0MQ by default does not give you visibility into those edge cases that you have to check.
Also, read the documentation upside down.
Backwards.
Because it starts off with this beautiful case that no one will ever use in production, ever.
Can I ask you some questions, actually?
So hang on, I've been given the 2-minute flag, the 1-minute flag, there you go. So, ta-da, there we go, so presentation. So I would love to take questions, but I think I only have about 30 seconds of questions, but I will be up at the front and I will be at the booking booth. And we can come and talk. So please come and talk, ask questions, just not while I'm standing here.